Kia ora, everyone. Thank you very much for joining us here today. My name's Nick Lauder, and yeah, we'll be talking about server-side request forgery and its journey into being included in the 2021 OWASP Top 10. First off, I'd like to thank all the sponsors for the event, especially thanking John and Austin for helping out getting all these talks up and running. Cool. Yeah, so my name's Nick Lauder. I work at Quantum Security. I'm one of the lead security consultants over there. My background used to be in software engineering, and then through a program called Summer Tech, I joined Quantum about 4 years ago, know nothing about security, and I just haven't left since. So for the next 30 minutes, there are 4 main points I want to cover. Go into a bit of what actually is server-side request forgery, shortened to SSRF. I'm going to talk a bit about the OWASP Top 10 and how it's been included. Then we'll go into impacts, and then as well what we can actually do to fix this vulnerability. Cool. Nice and easy. 2 different parts. Server side, something that the server does. Request forgery targets something from an unintended resource. So it can, in the simplest form, it can work in 4 different steps, 4 simple steps. So an attacker finds the vulnerable web server, and you can tell that it's vulnerable if there's something like a parameter. In this case, we've got URL under step 1, and there's a URL in the parameter. When the attacker sends that request to the vulnerable server goes, OK, I've now received a URL. I'm going to send a request to that URL. The target web server then responds to the vulnerable web server, where this is just an HTTP request. I'm just going to respond as expected. And then the vulnerable web server then forwards that response back onto the attacker. So in those 4 steps, the attacker does one action at the start. Then the vulnerable web server generates its own request. The target web server responds to the vulnerable server, and then the vulnerable server forwards that response back to the attacker. So I found a few examples of line, not of exploitable SSRF, but when it's actually by design, when this is like intended functionality. So the first one I found was in Microsoft Teams. So when you enter a link into your chat box, Microsoft then takes that link, they then go make a request to the web server, they generate an image for that, and then return the image back to you. So if you're in an organization that has a web proxy that isn't letting you get out into the internet, but you have an express route to Microsoft and you can still access Teams, you can actually get content through this SSRF. Even though it's an intended functionality and it's not necessarily exploitable, this was how they wanted the feature to be built. So we found this sort of by accident. We have an internal wiki at Quantum Security. We just noticed that when we put links into the chat box, we weren't getting any previews or images from it. And it turns out it's because Microsoft's making those requests. They can't access our internal wiki, so nothing was being generated. There's also a lot of sites that do website down checkers. So if you ever can't access a website, you're not sure if it's a you issue or it's a them issue, these websites will go and send requests on your behalf just to see whether it's actually down. In this case, if we check for localhost, so 127.0.0.1, that website down checker will then go request localhost. In this example, we found that it received a valid response, although because potentially no host name, there wasn't actually a website behind it, we just get the 403 forbidden error. But it shows that in this case, they didn't do any allow listing, deny listing, anything to stop a local request from being generated. And the third example is Google Translate. So Google Translate has the feature to translate entire websites for you. So the tool we've used here is called Burp Suite Collaborator. So this allows you to basically create a web server that's on the public internet, and then it monitors any requests that get sent to it. If we put the collaborator link into Google Translate, Google then reaches out, pulls that website, then tries to translate it and gives you the response. So this one is another one that if you're behind a web proxy that's blocking certain sites, malicious sites, but doesn't block Google, you can put the malicious links into Google. Google will then go request the information for you and return essentially the whole website. Cool. Now we're going to talk a bit about the OWASP Top 10 and the journey that server-side request forgery made to getting into it. So between 2017 and 2021, quite a few changes were made to the OWASP Top 10. A couple of new entries, a couple of merge entries, but the only one we really care about today is down the bottom, number 10. You'll also note that it's got an asterisk on it, and that means this was generated from community surveys, whereas traditionally OWASP uses data pulled from testing from partner organizations. This year, they reached out to the community, got their input from security experts, and they added some entries based on that. So server-side request forgery was the #1 most cared about vulnerability in the community surveys. During the data analysis that OWASP performs, they found that there's a very low rate of incidence. So only 2.72% of applications that they tested were found to have any sort of server-side request forgery vulnerabilities. And we'll also note that SSRF is the only individual vulnerability left on the OWASP top 10. So OWASP has groups such as injection. Injection includes cross-site scripting, SQL injection, external entity injection. But with server-side request forgery, it is its own vulnerability. So some of the statistics that OWASP has gathered on SSRF, the partner organizations tested for SSRF in about 2/3 of the applications, and this is above average test coverage. What they found, though, is only 2.7% of those applications actually had any vulnerabilities, which is under average that they noted. What they also found that when vulnerabilities were found, there was above average exploit scores and impact scores. So what does this mean? Lots of places are testing for SSRF, but very few places are actually finding it. But when people are finding it, there's quite a high impact, and we'll get into some of those impacts just a little bit down the line. So 2021 was new for OWASP because it started using metrics and community feedback. So the metrics are based on testing data. This is huge amounts of data that their partner organizations are able to feed into them, gives them a huge amount of insight into the amount of different vulnerabilities that are being found in different applications. The community surveys was based on more real-world experiences. So this was when they reached out to security architects, engineers, consultants, to find out what they're seeing a lot of, what they care about a lot, and then how could they incorporate those results into a 2021 top 10. So what we found is that making use of the metrics and the community surveys allows OWASP to leverage the huge amounts of data that they do have access to, but it also includes newer vulnerabilities that tooling isn't necessarily set up to find. So although SSRF isn't a new vulnerability in its own right, it's not something that is often cared about or thought about in automated tooling. So by using those community surveys, they can still highlight vulnerabilities that are worth noting that just aren't being automated for their searches. So what could go wrong? Before we showed 3 examples of SSRF by design, so here are some examples of why it is bad. So access localhost. So our second example, when we had the website down checker, we used the localhost as the example there. In this case, we're going to try access the localhost with an admin panel. So when web application administrator panels, often there won't necessarily be authentication for administrator pages because it's coming from their own machine. Why should you need to authenticate? In this case, the attacker sends the request asking for the localhost/admin. The vulnerable web server then just sends that request to itself. The endpoint receives it, and as it receives it, it's from itself, so it thinks, oh, this is fine. This is just myself looking at myself. So it responds as usual, but then the actual vulnerable application on the web server can then return that admin page. If there are a lot of get-based requests on that admin page, you can just add parameters to that URL and basically perform actions across the whole administrator site. You can also use it to access internal web applications. So if you've got a firewall on your network perimeter, an attacker on the public internet won't actually be able to access your internal web server. If you have your own web server sitting within your internal perimeter, you can send a request to that vulnerable server, and then that vulnerable server, because it's within the same network, is able to reach other internal services. If the authentication isn't being used on admin pages for internal services, because again, you're trusting the network position, they may be able to do similar things with the local host where you can access administrator pages just and bypass the firewall. Denial of service. So internet-facing applications will often have protections in place to protect against denial of service attacks. Internal web applications may not. If it's never going to be touched by the internet by design, why would you spend time, money, and effort protecting against denial of service? If you're able to send a large amount of requests to the vulnerable web server, and then the vulnerable web server forwards on requests one-for-one to an internal web app, you could end up overloading the internal web app, resulting in a denial of service attack. There are several different protocol schemas you can end up using with SSRF. So most of the examples we looked at already are web protocols, so using HTTP and HTTPS, but there's actually quite a lot of other protocols that commands like curl will interpret for you. In certain frameworks, they may end up just using command line type functions in order to actually make these requests. So some of these different protocols include things like file. So if you just wanted to read local files on the web server, if you return the Etsy password file, it's a clear indication that you're getting that local file inclusion. FTP, if there are other internal FTP servers scattered throughout the network, you can communicate with those. LDAP, Gopher, and DECT, all different protocols that allow you to communicate in different ways across internal networks. The combination of the different protocols really broadens the types of attacks and the types of data that could be retrieved using an SSRF vulnerability. Cool, so a lot of people here are developers. We will care about how do we actually fix some of these things. So the examples that we showed before was just a URL parameter, and you include the URL within that parameter. Does that input actually need to be customizable? In some cases, if your web application will only ever be reaching out to one other web application, could it be hard-coded? If there are a range of different web apps, but you know about them all, can you have references that you store on the back end and then just use an identifier to then call them from the front end? You can also use hostname or IP allow listing. So this is a common one to make sure that user can only request access to hosts that you are aware of, that you know about, and that is by design what's meant to happen for the application. You can also use hostname IP deny listing. So this would be used to specifically deny certain hosts. So a common one for this would be denying the private IP address range. So making sure that if someone were to make an SSRF request, they wouldn't be able to access any of your internal services, but you may want them to still be able to reach out to the rest of the internet. So you can limit the input to the specific hostname or IP address itself. So the example we showed before had the full HTTPS with the hostname/path. Could you limit this to just a specific hostname, and that's the only parameter they give? By doing this, they wouldn't be able to change that schema from HTTPS to something like file, and they wouldn't be able to access pages that aren't the intended design. You can also disable unused schemas. This will be likely a feature of whatever framework you're using. The commands may have controls to stop certain protocols actually being accessed with them. So if you only ever need GET requests from like a REST API, why would you need to enable file, FTP, LDAP, Gopher, DECT, all those things? Always enforcing authentication. So a few of the examples we had were either accessing localhost admin pages or internal service admin pages. A lot of systems will be insecure by default, and that's because if you're in a development environment, it can't actually be accessed from the internet. Why would you go through the trouble of trying to add authentication, ensuring all those, especially when you're in a debugging environment and you just want to fix your issues? If you ensure that all privileged actions are authenticated following a model such as Zero Trust, then the attacker won't be able to customize the URLs that they're using in a way because you won't be able to authenticate with whatever site the attacker's choosing. There's no perfect way to fix SSRF, especially it is by design. So in the end, network segregation. So instead of just using a flat network internally, you can have things like a DMZ, so demilitarized zones. That's where you put your public-facing web applications, and then any other internal services, such as databases, other web apps, they can sit in your internal zone. And if there's no real need for those to communicate, you can have network-level controls to prevent them. Because there's no one way to fix SSRF, our recommendation is always going to be defense in depth, so implement as many as you can. Cool. Speed run that a bit, but thank you very much, everyone, for coming. So quantum security, we do a lot of penetration testing and find these sort of things in the wild. We do have roles open all the time, so if you ever want to start looking at security, we don't need you to be experienced. We hire everyone from entry level up to principal. Feel free to come have a chat or get in touch after the talk. Does anyone have any questions?
Any questions for Nick?
In a situation where, let's say, there is authentication, so the backends have authentication, there's been some situations, like with Google, where they attach an authorization bearer cookie, and they use, you can use Collaborator to maybe try to steal that cookie. In those types of situations, what would be your recommendation for effects?
Cool. Yes, that's a good question, and it's something that I haven't seen in the wild before, but we've definitely discussed internally. So if you have a application that your vulnerable web server actually talks to, and you are authenticated, that request is going to include the credentials for that request. If you're able to convince the vulnerable server to talk to a host that you own, the vulnerable server will end up sending the credentials to the host that you own. So this ticks the box of, yes, you are authenticating internally, but there's all the other controls, such as like the allow listing is always what I would say is the best way to handle this, because you've got a specific subset of hosts or IP addresses that by design you do want to communicate with, so you're only actually going to end up sending things to that. The problem with allow listing and a deny listing as well is that people could bypass this. If you're using regular expressions, things like that, there are certain quirks with different regular expression systems. People may be able to find bypasses. So then you want to add things like network segregation. If the vulnerable server is intended to talk to internal services and not meant to go out to the public, then you can stop that. If you have a firewall in place, you can control the traffic that's originating from your web services. So defense in depth is the answer.
Cool, thank you. Any other questions? No? All right, thank you very much. Let's go a round of applause.
Awesome, thank you.